Welcome to Chemistry, Buffer Solutions, and the Henderson-Hasselbalch equation. Break time during 0.5 Cess, Brach's, data by Hertz are among the most important concepts in chemistry and biology. They resist changes in pH when small amounts of acid or base are added, making them essential for maintaining stable conditions in everything from laboratory experiments to the human bloodstream. B gave Henderson-Hasselbalch's equation. In this presentation, we will explore what buffers are, how they work using Le Chatelier's principle, the famous Henderson-Hasselbalch equation that lets us calculate buffer pH, different types of buffers, buffer capacity, common buffer systems, and their biological importance. Free time equals 0 to 3 Cess. Through 5 quiz questions and 5 fully worked problems, you will gain mastery of this essential topic. What is a buffer solution? Break time equals 0 to story Jane. A buffer solution is a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid, that resists changes in pH when small quantities of a strong acid or strong base are added. The key is that both components must be present in significant and roughly equal concentrations. The weak acid HA can neutralize added hydroxide ions, while the conjugate base A- can neutralize added protons. This dual action is what gives buffers their remarkable pH stability. Buffers work through Le Chatelier's principle. Break time equals 0.5 Cess. Consider a buffer made of acetic acid and sodium acetate. The equilibrium is CH3COOH plus water in equilibrium with H3O plus and CH3COO minus. 4 Cess required base S. When we add a strong acid like HCl, the extra H plus ions react with acetate ions to form undissociated acetic acid, shifting the equilibrium to the left. When we add a strong base like NaOH, hydroxide ions react with acetic acid to form acetate and water, shifting the equilibrium to the right. In both cases, the pH change is minimal. The buffer's ability to resist pH change depends on having roughly equal concentrations of the weak acid and its conjugate base. The Henderson-Hasselbalch equation is derived directly from the Ka expression. Transformation to significant lactameters to take the motion alone 0 and 5 Cess, starting with Ka equals H plus times A minus divided by HA. We solve for H plus, then take the negative log of both sides. Because what ups the most 1 times slash data. This gives us pH equals pKa minus log of HA over A minus, which we rewrite as pH equals pKa plus log of A minus over HA. This equation is powerful because it relates the pH of a buffer directly to the pKa of the weak acid and the ratio of conjugate base to acid concentrations. Lawrence Henderson derived the bicarbonate buffer equation in 1908. And Carl Hasselbalch re-expressed it in logarithmic terms using Sorensen's pH concept in 1917. Buffer solutions come in 2 main types. Break time equals 0.4 S. Acidic buffers have a pH less than 7 and are made from a weak acid, and its salt with a strong base. The classic example is acetic acid and sodium acetate, with pKa of 4.76 and an effective pH range of 3.8 to 5.8. Break time equals 0.4 S. Basic buffers have a pH greater than 7 and are made from a weak base and its salt with a strong acid. The classic example is ammonia and ammonium chloride, with a pKa of 9.25 and an effective pH range of 8.25 to 10.25. Break time equals 0.4 Cess. A buffer can also be made from a very weak acid like HCN with pKa of 9.3 and its salt NaCN, producing an alkaline buffer. Break time equals 0, 3S. The effective pH range for any buffer is approximately pKa plus or minus 1. Buffer capacity is a quantitative measure of a buffer's ability to resist pH change. Break time equals 0. 4 Cess. The maximum buffer capacity occurs when the pH equals the pKa of the weak acid, which is when the concentrations of the weak acid and conjugate base are equal. Extend 3. At this point, the ratio of A minus to HA is 1 and log of 1 is 0, so pH equals pKa. Break time equals 0, Streesa's Snyder. The buffer capacity falls to about 33% at pH equals pKa plus or minus 1, and to only 1% at pH equals pKa plus or minus 2. Website when the United States at impos of UFund and forces. The maximum amount of strong acid that a buffer can neutralize equals the number of moles of conjugate base present. The maximum amount of strong base equals the number of moles of weak acid present. Increasing the total concentration of buffer components increases the buffer capacity. Several buffer systems are frequently encountered in chemistry and biochemistry. The acetate buffer using acetic acid and sodium acetate has pKa of 4.76 and is used in biochemical research and food preservation. Break time equals 0. 3s. The phosphate buffer using dihydrogen phosphate and hydrogen phosphate has pKa of 7.21 and is the primary intracellular buffer in biological systems. Break time equals 0. 3s/changer de bicarbonate buffer using carbonic acid and bicarbonate has pKa of 6.37 and is the primary blood buffer system. Break time equals 0.4. SAST grids buffers are a series of zwitterionic buffers developed specifically for biochemistry, including MES, pipes, MOPS, HEPS, and TRIS. Each has minimal metal ion binding and minimal temperature dependence, making them ideal for cell culture and enzyme studies. Buffer systems are absolutely essential for life. Break time equals 0.4 says, quote, human blood must maintain a pH between 7.35 and 7.45 for enzymes to function properly. This narrow range is maintained primarily by the bicarbonate buffer system, which is an open system linked to the lungs. To the Corpquartz-Face-Mox 0.4 buffer system, the equilibrium is CO2 gas in equilibrium with aqueous CO2, which reacts with water to form carbonic acid, which dissociates to bicarbonate and H+. 1.4s. H drops. When blood pH drops, we breathe faster to exhale more CO2, shifting the equilibrium and reducing H+. Break time equals warp period. Reducing when blood pH rises, we breathe slower to retain CO2. The kidneys also regulate bicarbonate levels over hours to days. Break time equals 0 to 3 say/diabetic ketoacidosis cause deep, rapid breathing called Kussmaul respirations as the body tries to compensate for metabolic acidosis. Quiz question 1. Break time equals 0.5 s. Join of the following mixtures will make a buffer solution. Break time equals 0.6 s. Stored from option A, HCl plus NaCl. Break time equals 0. 4 s/Janab option B, CH3COOH plus CH3COON A. Break time equals 0.4 s. Source option C, NaOH plus NaCl. Break time equals 0. 4s/HNO3 plus NaNO3. Break time equals 1c. Take your time to think about this. Break time equals 8. The correct answer is option B. A buffer requires a weak acid and its conjugate base. Option B, acetic acid and sodium acetate, is a classic buffer. The weak acid CH3COOH and its conjugate base CH3COO- are both present. HCl, NaOH, and HNO3 are strong acids or bases and cannot form buffers with their salts. Quiz question 2. Break time equals 0.5 s. Join us the Henderson-Hasselbalch equation. Break time equals 0.6 s/join us pH equals pKa plus log of HA. Break time equals 0.4 s. Option B, pH equals pKa minus log of A minus. Break time equals 0.4 s/join us equals pKa plus log of A minus over HA. Over A minus, think about the derivation from Ka. Break time equals pKa plus log of HA over A minus. Think about the derivation from Ka. Break time equals 8. The correct answer is option C. The Henderson-Hasselbalch equation is pH equals pKa plus log of conjugate base concentration divided by weak acid concentration. It is derived from the Ka expression by taking the negative log of both sides and rearranging. Option D has the ratio inverted. Quiz question 3. Break time equals 0.5 SAS minus Tate buffer has equal concentrations of acetic acid and acetate ion. If pKa equals 4.76, what is the pH? Break time equals 0. 6S for bicarbonate 0, option A, 4.76. Break time equals 0.4 SAS for bicarbonate, option B, 7.00. Break time equals 0.4 SAS, option C, 3.76. Break time equals 0, 4 SAS, direct, option D, 5.76. Break time equals 1 SAS. Think about what happens when the concentrations of acid and conjugate base are equal. Win for value, practice HT. The correct answer is option A, 4.76. When A concentration equals A minus concentration, the ratio is 1 and log of 1 is 0. Therefore, pH equals pKa plus 0, which equals pKa itself, 4.76. This is also the point of maximum buffer capacity. Quiz question 4. Break time equals 0.5 C. What is the effective pH range of a buffer with pKa equals 7.21? Break time equals 0.6 S slash option A, 6.21 to 8.21. Break time equals 0, 4 S slash Jandow to SMB, 7.21 to 8.21. Break time equals 0.4 S slash option C, 6.21 to 7.21. Break time equals 0.4 S, option D, 5.21 to 9.21. Break time equals 1 S. Remember the rule for effective buffer range. Only fruit and extra pH range. The correct answer is option A, 6.21 to 8.21. The effective pH range of a buffer is approximately pKa plus or minus 1. For pKa equals 7.21, this gives a range of 6.21 to 8.21. Within this range, the buffer capacity is at least 33% of maximum. A phosphate buffer with this pKa is effective in this range. Quiz question 5. Break time equals 0.5 SAS. A buffer has 0.10 molar NH4 plus and 0.20 molar NH3. What is the pH? The pKa of NH4 plus is 9.25. Break time 0.6 S, force 5, option A, 895. Break time equals 0.4 S slash option B, 9.25. Break time 0.4 S slash option C, 9.55. Break time equals 0.4 S dash option D, 9.85. Break time equals 1 S. Apply the Henderson-Hasselbalch equation with these numbers. Break time equals 8. The correct answer is option C, 9.55. Using Henderson-Hasselbalch, pH equals 9.25 plus log of 0.20 over 0.10, which equals 9.25 plus log of 2, which equals 9.25 plus 0.30, giving 9.55. This is a basic buffer with pH above 7. Problem 1. Acetate buffer pH. Break time equals 0.6 s/J to buffer is made by dissolving 10.0 grams of sodium acetate in 200.0 milliliters of 1.00 molar acetic acid. Ka equals 1.7 times 10 to the negative 5. Calculate the pH. Break time equals 0 data step 1. The molar mass of sodium acetate is 82.03 grams per mole, which is 0.1 step 2. Moles of sodium acetate equals 10.0 grams divided by 82.03 grams per mole, which is 0.122 moles. Moles of acetic acid equals 1.00 molar times 0.200 liters, which is 0.200 moles. Break time equals 1 s. Step 4. pKa equals negative log of 1.7 times 10 to the negative 5, which is 4.77. Plug into Henderson-Hasselbalch. pH equals 4.77 plus log of 0.122 over 0.200, which is 4.77 plus log of 0.61, which is 4.77 plus log of 0.61. Which is negative 0.61 is negative 0.215. The pH equals 4.77 minus 0.215, which is 4.56. The answer is pH equals 4.56. Problem 2. Ratio for desired pH. Break time equals 0.5 s. What ratio of NH4 plus to NH3 is needed to prepare a buffer with pH equals 9.0? The Ka for NH4 plus is 5.6 times 10 to the negative 10. Break time equals 0.8. Step 1. pKa equals negative log of 5.6 times 10 to the negative 10, which is 9.25. Plug into Henderson-Hasselbalch. 9.00 equals 9.25 plus log of NH3 over NH4 plus. Step 3. Rearranging gives log of NH3 over NH4 plus equals 9.00 minus 9.25, which is negative 0.25, which is 0.56. Step 4. NH3 over NH4 plus equals 10 to the negative 0.25, which is 0.56, which is 1.56, which is 1.56, which is 1.79. This means we need almost 1.8 times more ammonium. This means we need almost 1.8 times more ammonium ion than ammonia. Problem 3. Buffer after adding strong acid. Break time equals 0.5 s/Janjip 50.0 milliliters of 0.1 Tage molar HCl is added to a buffer containing 0.025 moles of acetate and 0.030 moles of acetic acid. Ka equals 1.7 times 10 to the negative 5. Find the new pH. Know your liters times step 1. Moles of HCl added equals 0.0500 liters times 0.100 molar, which is 0.00500 moles of H+. Through your first two, weak list as RS. Step 2. The added H+ reacts with acetate to form acetic acid. Acetate decreases. Acetic acid increases. Break time equals 1 s. Step 3. new acetate equals 0.025 minus 0.005, which is 0.020 moles, which is 0.030 plus 0.00 plus 0.005, which is 0.035 moles. Step 5. Apply Henderson-Hasselbalch. pH equals 4.77 plus log of 0.020 over 0.035, which is 4.77 plus log of 0.571, is negative 0.243. The pH equals 4.77 minus 0.243. The pH equals 4.77 minus 0.243, which is 4.53. The pH only dropped by 0.03 units, demonstrating the buffer's effectiveness. Problem 4. Buffer after adding strong base. Break time equals 0.5 ses. A buffer has 0.0400 moles of NH3 and 0.0250 moles of NH4 plus. Add 20.0 milliliters of 0.75 molar NaOH. Find pH. Ka of NH4 plus is 5.6 times 10 to the negative 10. Rake time equals 0.8. Step 1. Moles of NaOH added equals 0.0200 liters times 0.75 molar, which is 0.0150 moles of OH minus. Mixture provision is specially a quarantine. 1 ses for form. Step 2. The hydroxide reacts with NH4 plus to form NH3 and water. NH4 plus decreases, NH3 increases. One reason we see to be instructed, use 3 to 5 extremes. New NH4 plus equals 0.0250 minus 0.0150, which is 0.0100 moles, plus 0.0150, which is 0.0400 plus 0.0150, which is 0.0550 moles. So 10 to the negative 10, which is 9.25, pKa equals negative log of 5.6 times 10 to the negative 10, which is 9.25. Step 6. pH equals 9.25 plus log of 0.0550 over 00, which is 9.25, plus log of 5.50, which is 9.25 plus log of 5.50. Log of 5.50 is 0.740, so pH equals 9.25 plus 0.740, which is 999. The answer is pH equals 9.99. Problem 5. Buffer capacity calculation. Break time equals 0.5 ses store gained. A buffer contains 0.35 moles of HCO3 minus and 0.50 moles of CO3 minus. What is the maximum strong acid or strong base that can be added? CO3 minus is the weak acid, and CO3 minus is the weak acid, and CO3 minus is the conjugate base, which is CO3 born mated primitivity 0.5/. Step 2. The maximum strong acid that can be added equals the moles of conjugate base, which is 0.50 moles. Rake times equals 1 ses. Step 3. Adding more H plus would consume all the CO3 minus, converting it to HCO3 minus, and the buffer would be exhausted. Break time equals 1 ses. Step 4. The maximum strong base that can be added equals the moles of weak acid, which is 0.35 moles of OH minus. Step 5. Adding more OH minus would consume all the HCO3 minus, converting it to CO3 minus. The answer is maximum acid is 0.50 moles of H plus, and maximum base is 0.35 moles of OH minus. Let us consolidate everything we have learned about buffer solutions and the Henderson-Hasselbalch equation. Break time equals 0.5 says a buffer is a mixture of a weak acid and its conjugate base that resists pH change. pH equals pKa plus log of conjugate base over weak acid.